Ah, yes, excellent question. So, I think I have one. I have something perfect for that. Sure. So, for example, someone could say something like, find the, I should write the top thing I use right here. This is code 21A. Today is the 29th or the 30th? 29th. So we said find the average rate of change I should say, f of x equal to x squared plus 4x on the interval from 1 to 3. Here's how we do that. So you don't really, in fact, I'm going to do it without drawing the graph, and then I'll draw the graph to kind of give context. But very, very broadly, average rate of change is just the slope of the secant line. So it's essentially your average rate of change is your change in y divided by your change in x. Or in this particular example, it's going to be f of 3 minus f of 1 divided by 3 minus 1. Because what we're doing there, if you graph this, x squared plus 4x looks nominally like this, right? So here's 1, here's 3. So basically, there's f of 1, there's f of 3. It's the difference in the y's divided by the difference in the x's, or said another way, the slope of the secant line. So it's the slope of the line connecting those 2 points. So look at me, I drew it pretty well. As far as calculating it, not too terrible. We plug in 3 and 1. Let's see, f of 3 is going to be 9 plus 12. F of 1 is going to be 1 plus 4 divided by 2. So it's going to be 21 minus 5, which is something. I think it's 16. 16 over 2, which is 8. Which is the easier thing to calculate when it comes to a question like this. Certainly, the average rate of change is usually the thing that requires less effort to calculate. If they then asked us to, say, find the instantaneous rate of change, is that how you said it, or was it like phrased differently?
Yeah.
Okay. Yeah. The instantaneous rate of change. We have to be given a specific point. So I think valid choices for this problem would be find the instantaneous rate of change either at 1 or 2 or 3. I think most likely the question would be at 1, just because we often think about like finding the slope of the secant line and then letting the right-hand point come closer to the left-hand point so that you get the slope of the tangent line. That's kind of it. As far as calculating it, so let's do this. So find the instantaneous rate of change at x equal to 1. So, plus you. The idea is the same thing, except that instead of finding the slope of the secant line between 1 and 3, we're going to find the slope of the secant line between 1 and 1 plus h. So we're finding the slope of that line there, which is not drawn great, but such is life. And then we're going to let h, well, I should say, we're going to let 1 plus h get closer and closer to 1 by taking the limit as h approaches 0. So to find the instantaneous rate of change, it would be the limit as h approaches 0, in this case of f of 1 plus h minus f of 1 divided by 1 plus h minus 1, which again, obviously the bottom is going to be h, but I like to write it this way so it really kind of emphasizes the fact that we're still finding the slope of a thing. And then we just do the calculation. So, all right, it's going to be the limit as h goes to 0. Your f of 1 plus h is going to be 1 plus h squared plus 4 times 1 plus h minus f of 1 is still the same as it was before. It's still 5. On the bottom, our 1 plus h minus 1 is just h. And when it comes to instantaneous rate of change like this, we know that our ultimate goal, well, our ultimate goal is to find the answer. But like the thing that's going to get us there is making sure that this h cancels out by making sure that all the not h things in the numerator cancel out. So here, what ends up happening is we get the limit as h approaches 0 of 1 plus h squared multiplies out as 1 plus 2h plus h squared. Distribute the 4, you get 4 plus 4h minus 5 divided by h. And the 1 plus 4 minus 5 is 0. Everything left has an h in it, so we divide each thing by h, and we get the limit as h goes to 0 of 2h divided by h is 2, h squared divided by h is h, and 4h divided by h is 4, and then let h go to 0, so you get 2 plus 0 plus 4, which is 6. So that's your instantaneous rate of change, or the slope of your tangent line at 1. Fair question. Other question? Yeah, sure.
We can talk about it. Because on the thing, they asked for the average rate of change in ours, but they gave us 3, 3 plus h.
Okay,
So
sure.
we're like really trying.
So they're definitely building you up towards this, right? So basically they're having you find that first, the 2 plus h plus 4, which is 6 plus h. And then after you found that, then you're letting h go to 0 if you're finding the instantaneous rate of change. Yeah. So it's a good question. I like that.
Right, it's writing the limit. Technically.
Right, totally, yeah. So, right, I would say very kind of generally, and this totally plays into what we're about to talk about. Generally, the average rate of change between, will be very, very generic here. X, I should say not, let's say instead of between, on the interval from x to x plus h is given by what you just said, f of x plus h minus f of x divided by x plus h minus x. And then if you wanted the instantaneous rate of change, it's literally just taking the limit of that. So the instantaneous rate of change at x is given by the limit as h approaches 0 of your f of x plus h minus f of x all divided by h. X plus h minus x. Same difference. Yeah. And I'll even say more. This is our definition of the derivative, right? So just to kind of really, I forget, there's a saying I was trying to think of. I don't remember what it was. Just to really paint the picture, not what I was trying to go for, whatever. The derivative of f of x is defined as the limit as h approaches 0 of exactly that, f of x plus h minus f of x all divided by h. I still think be a little bit more specific, the derivative as a function, right? So the derivative f of x as a function versus the derivative at a particular point. Cool. Which is kind of where we're at now, right? Talking about derivative functions. I feel as you're looking at your week 4 highlights here, I am guessing you all have talked about or are going to talk about tomorrow in your class lots of different derivatives, like formulas. Should we start there? I kind of feel like we should do it. So let's talk about a couple things before we get straight into it. But let's kind of, yeah, we'll go that way. Let's say that we wanted to find, and so certainly at this point, I feel like we're moving away from find the derivative of the point. Or more generally, if you were asked to find the derivative of a function at a point, you should still find it as a function and then just plug in the points. So we're going to find the derivative of f of x equal to x cubed. And then we might ask and answer some other questions after that. All right, so there's lots of notation for the derivative. There's probably like, oh, I think your instructor even wrote a bunch of them. Your instructor wrote like, where'd they go here? Sorry, I had notes. Where is that? Yeah, 1, 2, 3. Your instructor wrote like 6 different notations for the derivative here. Okay. I would say the pretty typical ones we use would be f prime of x, or df dx is actually not super typical. It's more typical to write dy dx because you're kind of f and y are kind of interchangeable. But either way, we're just going to throw the definition at it. It's going to be the limit as h goes to 0 of f of x plus h minus f of x divided by x plus h minus x, which I will start writing as just h. But it's a good reminder that it's really just the difference in the y's divided by the difference in the x's, or the slope, or the limit of the slope. Okay, so now we actually have to do the thing. So we have the limit as h approaches 0. See, f of x plus h is just going to be, instead of x cubed, it's going to be x plus h cubed. F of x is just x cubed, all divided by h. And again, our goal is the same as it was last time. We're still trying to make that bottom h cancel out so then we can substitute in 0 for the rest of the h's that are left over. And this is where I'll remind you of the thing we talked about on Tuesday. Pascal's triangle is super useful when you're trying to expand out x plus h to some positive integer power, like 3 or 4 or 5. So quick reminder, Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Oh, x plus h cubed is going to be 1x cubed plus 3x squared h plus 3xh squared plus 1 h cubed minus x cubed divided by h. And then we can, well, the x cubed minus the x cubed is 0. Everything else has an h in it still, so we divide each thing by h. So we can rewrite this as, I personally prefer to factor out an h from the top. So if it were me doing it, which I guess it is, I would probably choose to write it as limit as h goes to 0. On top, I'm going to have h times 3x squared plus 3xh plus h squared, all divided by h. And then the h is divided to 1. So I think you can probably skip the step that I'm writing here. Limit as h goes to 0 of 3x squared plus 3xh plus h squared. And then you plug in 0 for h and you get 3x squared plus 0, which is just 3x squared. Or to write it very clearly, for f of x equal to x cubed, the derivative is equal to 3x squared. I will point out my favorite way of writing this is the following, which I guess you should get used to because I'm probably going to write it like this most of the time. Not like this, the way I'm about to write. So I like to write the derivative d dx of my function x cubed is equal to 3x squared. To me, this is a more compact, nice way of writing all the information at once, right? The function I'm taking the derivative of is x cubed, and when you take the derivative of that x cubed, you get 3x squared. That's how I would write it personally. So, what about a higher power of x? What if we were going to do x to the fourth? Let me actually ask you all, have you guys talked about the power rule yet? Cool. So what if I want to find the derivative of x to the fourth power? And again, this is how I like to write it, d dx of the function. You can write the x to the fourth in the, I hesitate to say numerator, because technically d dx is not a fraction. But I'll tell you truthfully, dy dx or d dx or something, even though it's not a fraction, it pretty much acts like a fraction in every way you would want it to. So even though dy dx or d dx of your derivative of your function isn't a fraction, we often treat it like it is one and manipulate it like it is one. So what I was saying here is you could, although it's real weird, you could write this as dx to the fourth dx, but that does not feel good to me. I would not encourage anyone to write it like that. Although we do certainly write something like dy dx or df dx. I will also point out, because this is just something I've noticed over the years, how do we say this? Here's what well, I don't even want to put it in your minds to say the wrong thing. The way we say this is dy dx. There is no word like over because it's not a fraction. So we do not say dy over dx. We say dy dx or df dx or d whatever the function is dx. That might just be a pet peeve on my part, but I want to encourage everyone to say math correctly. So I'm going to say it the right way and let you know about some of the things you might not know. All right, so anyway, go ahead and write down the limit definition. The limit is h approaches 0 of, the first part you want unsimplified. Making that clear. So here we should have the limit as h goes to 0 of our x plus h to the fourth power minus, I gave myself way too much room there, x to the fourth all over h. And then we're going to do the same thing we did last time. In fact, I'm going to go back to my previous page here for a second and write down the next line of Pascal's triangle, 1, 4, 6, 4, 1. So those are going to be my coefficients. So it's going to be, when I expand this out, the limit as h goes to 0 of 1x to the fourth plus 4x cubed times h plus 6x squared times h squared plus 4x times h cubed plus 1 times h to the fourth minus x to the fourth, all divided by h. And then the same sort of thing that happened before is going to happen again. We're going to make sure that the x's subtract to 0. Everything left has an h in it. I'm going to factor out the h because that's the way I like to write it. Actually, let me not do that. So let me show you how you could probably do this, showing maybe the least amount of steps if you wanted to. So from here, if you really didn't want to write this out more than you had to, I would say it'd probably be fine to also cancel the h's. So I'm going to say 4x cubed h divided by h is 4x cubed. 6x squared h squared divided by h is going to be 6x squared h. And every term just has one less h than it had before. So it's going to be plus a 4x h squared plus an h cubed. And then I'm going to plug in 0 for every h. So I'm going to get 4x cubed plus 0 plus 0 plus 0. That's probably reasonably the least amount of work you can show if you're asked to do this problem the long way. And so you might start to notice the pattern. The derivative of x to the fourth was 4 times x to the third, and the derivative of x to the third was 3 times x squared. You might have a good guess for what the derivative of x to the fifth is going to be. I was numbering things here. Write down your guess. You don't have to share it with me. I won't ask you what your guess is, but I want you to write down what your guess is. This is the last one we're going to do the long way for this. Well, the last one with a specific number we're going to do the long way. So back to my Pascal's triangle over here. While you guys write out your guesses. Pascal's triangle, let's see, 1, 5, 10, 5. Sorry, 10, 10, 5, 1. So let's see here. We're going to get the limit as h goes to 0 of x plus h to the fifth plus, sorry, not plus, minus. So I'll point out, I think, and I haven't been doing this the last couple times because I kind of started myself out with the function, but I would say usually when I have a function, I like to actually just write down the definition again. So like when I'm starting off, I'm like, oh yeah, my derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. I kind of like to remind myself of that every time I'm doing it, really. So that shouldn't be a plus sign there. That should be a minus sign there. It's a big minus sign. X to the fifth, all over h. Okay, we're almost there, I promise. So taking this limit, interesting, I wonder what that was about. Anyway, taking this limit, we get, well, if we multiply this out, it's going to be x to the fifth plus 5x to the fourth times h plus 10x cubed h squared. Again, we're just using the coefficients from Pascal's triangle, and then every next term, the power of x decreases by 1, the power of h increases by 1. So the next one's going to be 10x squared h cubed plus 5x h to the fourth plus 1 times h to the fifth minus that x to the fifth over there. All divided by h. And then the x to the fifth subtract to 0. I'm going to factor out an h, even though I feel like it's maybe not necessary. Factoring out the h, we have a 5x to the fourth plus a 10x cubed h plus 10x squared h squared plus 5x h cubed plus h to the fourth. This h divides that h to 1, and you're left with a 5x to the fourth plus a lot of zeros. So I imagine many of you probably guessed that already. Great. You might also then guess that the derivative of, say, x to the 80th power is definitely not one we're going to multiply out, right? Because there'd be like 81 terms, and finding that row in Pascal's triangle is a lot of effort in its own. but you probably reasonably guess that the answer is going to be 80 times x to the 79th power. And it is. I do feel so. See, most of the time in this class, I do like to offer kind of support for why a thing is true. Occasionally, specifically L'Hopital's rule later on, I might be a little hand-heavy with because proving it is kind of a giant pain. But this power rule, which is what it's called, is relatively easy to prove. So let's talk about it. So for Pascal's triangle, again, here we go. Notice that every time we write a row, well, and again, starting with the top row being called the 0th row, and then the first row, and then the second row, whatever row number we're at, the second number in that row is the same as that row number. So if you're in the 4th row, it's 1, 4, something, something, something. If you're in the 5th row, it's 1, 5, something, something, something. If you're in the 80th row, it's 180, something, something, something. And honestly, the first two numbers are all we really actually need to know. So what if I wanted to find the derivative of x to the power of n? Well, I would need the nth row. And in the nth row, it's going to be 1 and other things. So we're going to write this as the limit as h goes to 0 of x plus h to the nth power minus x to the nth power divided by h. And just so things don't get too messy, I'm going to say that our coefficients are 1 and then n and then some c2 and then some c3 all the way to some c sub n and the last one will be a 1. In fact, the second to last one will also be n, right? There is symmetry here. So if you really want to say this one is actually also n, not that we really care. So multiplying this out, x plus h to the n is going to look like 1 times x to the n plus n times x to the n minus 1 times h plus whatever this coefficient is here, c sub 2 times x to the n minus 2 times h squared plus c sub 3 times x to the n minus 3 times h cubed plus a bunch of things until the very last two are n times x to the first times h to the n minus 1 plus h to the nth power. And be careful when you're writing this, make sure your h's look different than your n's. My h's sometimes start to look like my n's, so be careful. So here, we can see that when we write this out, I probably should have written it down here because I'm going to write it twice. We're going to get the limit as h goes to 0 of x to the n plus n times x to the n minus 1 times h plus c2 times x to the n minus 2 times h squared. I'm going to skip right into the next one and go all the way to the last couple. The last couple are n times x times h to the n minus 1 plus h to the nth power, all divided by h. And just like the previous times we've done this, the same sort of thing's going to happen. I forgot one thing. The minus the x to the n. It's making noise over here. Sorry. I don't know what's making. Something's making noise. It's bothering me a little. I'm probably getting emails. Let me close my email. Sorry, as I mentioned before, they gave me a new laptop and some of the things are a little bit different on it. So occasionally there's weirdness that I'm not aware of. Trying to get sorted out. Anyway, just like before, the x to the n minus x to the n is 0. Every remaining term has an h in it. And when I divide each thing by h, the first term won't have an h anymore, but every other term will still have an h. So when we simplify this, we're going to get the limit as h goes to 0 of n times x to the n minus 1 plus c2 times x to the n minus 2 times h squared divided by h is just h to the first, plus a lot of other terms that all have higher powers of h up until the last couple of terms are going to be an n times x times h to the n minus 2, because they took away one of the h's, plus an h to the n minus 1. But then, if we take the limit as h goes to 0, all of these terms are going to end up going to 0. So we end up with just n times x to the n minus 1, which is the power rule, essentially. So it is the case. Now, I'll say a couple things about this here in a second. Yeah, come on, paper, crack together. So it is the case that, let's call it the power rule here. So the power rule says that if f of x is x to, for some reason we usually use x to the p, either p or m, whatever letter you like to use. If f of x is x to the p, then the derivative f prime of x is p times x to the p minus 1. A couple things of note. We proved this, but we only proved it for powers that are positive integers because that Pascal's triangle expansion only works when your power is a positive integer. That said, the power rule is true even if p isn't a positive integer. Power rule is true for any real number p. So this derivative of x to a power is the power times x to the power minus 1 for any real number p. Even if p is something unexciting like 1 or 0, it still works. For example, if f of x is equal to x, well, you know what the derivative of x is already. What's the slope of the line y equals x? There's your derivative, right? If your function is a line, the derivative is just the slope of that line. But it also works if we use the power rule. If we think of this as x to the first, then your derivative is going to be 1 times x to the 1 minus 1, which is 1 times x to the 0, but x to the 0th power is just 1. So your derivative is 1. Should you do it this way? No. You should just be like, yeah, I know it's 1. You don't have to write, you don't need to show this work. Like no one's gonna be like, oh, how'd they know the derivative of x was 1? Because you knew the derivative of x was 1. Like you don't have to show work for that. In a similar way, if your function is a constant, like 1, or really any constant, but I'm gonna go with 1 here, we can say, well, a constant function is a horizontal line. Horizontal lines have what kind of slope? Right. So the derivative is 0. Or you could do it the longest way possible and say, well, this is really x to the 0th power. So then the derivative is going to be 0 times x to the 0 minus 1. But 0 times anything is 0, so we just get 0. Again, not what we like to do, but just wanted to point out that technically you can always use the power rule if you're taking the derivative of x raised to a power. Great. So, a couple more things to say about this before we get too crazy. It also is true for powers that aren't integers. For example, sure, aren't positive integers. For f of x equal to the square root of x, that is a function we can definitely take the derivative of using the power rule because really the square root of x is x to the 1/2 power. And the derivative is going to be 1/2 times x to the 1/2 minus 1, which I don't, well, first of all, we should definitely simplify the power. We should definitely at least write this as 1/2 times x to the negative 1/2. But that's not my favorite way to write it. Or I should say, it's not always the best way to write it. This is super useful, especially if you're going to have to take another derivative. Like maybe they're going to ask you for the second derivative or the third derivative. So if you're asking for multiple derivatives, certainly writing your root as a fractional power is the way to go. But if they ask me what's the domain of my derivative, writing like that doesn't help me a whole lot. It doesn't show me as much as I want to see. So I would much rather also think of this as 1 over 2 times x to the positive 1/2, or really actually 1 over 2 times the square root of x. Both of these ways are valid ways of writing it, and they're good for different reasons. So definitely get comfortable with going back and forth between these, because I do think being able to go back and forth between them is a useful skill. And it comes up often. Like I would say the derivative of the square root of x comes up often enough that you want to be able to be like, yeah, it's 1/2 x to the negative 1/2, and yeah, it's 1 over 2 root x. But how do we know it's really true? I mean, other than you believe me and I wouldn't lie to you, but like, how do we know the power rule actually works for this function? We know it works for positive integers, but that's not a positive integer. So I feel kind of compelled, or at least I owe it to you, to show you at least one where the power is a fraction, like this, and at least one where the power is negative, which we'll do in a second. So two more limit definitions for these power rules, and then we can be satisfied that the power rule really does work for any power. I know you believe me, or at least I assume you believe me. I hope you believe me, but let me give you a little more evidence. So let's actually find for f of x equal to the square root of x. Let's actually find the derivative using the limit definition, which we might have done before, or at least something like it, but it's never bad to do it again. So the derivative here is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h, which then we will write as the limit as h goes to 0 of the square root of x plus h minus the square root of x, all divided by h. And I imagine each and every one of you could tell me what the next step is that I need to do for this 0 over 0 type of limit. What am I multiplying by? Yeah. So square root of x plus h plus the square root of x over the square root of x plus h plus the square root of x. The usual thing happens, meaning that the parts that are conjugates in the numerator, in this case, multiply out to being the first thing squared minus the second thing squared. So it's going to be the square root of x plus h squared minus the square root of x squared. On the bottom, we don't multiply it out. We just leave it factored as h times the square root of x plus h plus the square root of x. You can see in the numerator that the x minus x is going to be 0. So we're left with the limit as h goes to 0 of h over h times the square root of x plus h plus the square root of x. The h's divide to 1. So then you're left with the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. Now that we've gotten rid of the problematic h in the denominator, every remaining h just gets to become 0. So we evaluate the limit. We don't write the limit anymore. We just get 1 over the square root of x plus 0 plus the square root of x. You can obviously skip this step, I think, and say, oh, I've got 1 over root x plus root x, which is 1 over 2 root x. Or if you prefer, 1/2 times x to the negative 1/2. As expected. Great, it works. Feel free to interject if you have questions. I feel like I'm talking a lot. I mean, I always feel like I'm talking a lot in this class, but like, if you have questions, comments, concerns, thoughts, please say words, ask questions. I feel like I'm just kind of going on and on and on. But that said, oh yeah, I know. So, I will point out, I won't do it, but I will point out, here's a fun, maybe not the right word. Here's a challenge question for you to occupy yourself with later on. Use the limit definition of the derivative to find the derivative of the cube root of x, or x to the 1/3, which is the limit as h goes to 0 of the cube root of x plus h minus the cube root of x, all divided by h. If you want a challenge, that's a challenging question. If you're curious about it, come see me in office hours. But moving on, let's look at one more limit definition example where we're going to do the work. So let's say, let's say this. So in a similar way, we can find the derivative of 1 over x squared. In fact, let's just throw the power rule out at first. So I really want to point out here, the derivative of 1 over x squared is not 1 over 2x. To be able to use the power rule, x has to be not in the denominator. It has to be just like x to a power, not 5 over x to a power, or 2 over x to, or 1, right? It has to be, this is the derivative of x to the negative 2 power. And so if we want to use the power rule, we can say, well, I'm going to negative 2 times x to the negative 2 minus 1, which is negative 2 times x to the negative 3rd, Or if you prefer, -2 divided by x to the positive 3. I feel like I said -1. I don't know. Anyway, the derivative is -2 times x to the -3 or -2 over x to the positive 3. But let's, maybe for the last time, use the limit definition. Definitely not the last time we're going to use limit. So the last time for the power rule, we'll use the limit definition here. So I will also say, kind of generally, when we talk about derivatives of functions, the first place you go to is like, well, it's a new function. Let's throw the limit definition at it and see what happens. Sometimes it works out great, sometimes less so. But here, we want to use the limit definition to find, sure, of the derivative of f of x equal to 1 over x squared. Well, it's going to be the limit as h goes to 0. I do, as I said before, I like writing it out this way. It's just a good, especially if you, maybe this is the first time you're taking calculus. If you, especially if it's the first time, I think it's good to write out this definition just a lot of times. So you're like, oh yeah, I know limit definition like the back of my hand. It's just there. It's always in my mind. It's f of x plus h minus f of x all divided by h. So then actually plugging in the function, your 1 over x squared, if I plug in x plus h for x, it's going to be 1 over x plus h squared minus 1 over x squared all divided by h. Okay, so we have fractions and fractions, which is never my favorite. A couple things we're going to do. For the top, we're going to get a common denominator. And for these problems, the common denominator is always going to be unwieldy. It's always going to be just multiply this fraction by that denominator over that denominator, and multiply this fraction by that denominator over that denominator. Like there's nothing else to do. There's no, you can't just get an extra h in there. You have to like do the whole thing. So here, I'm going to multiply this one by x squared over x squared, and this one by x plus h squared over x plus h squared. I know, right? Yeah, I feel the same way. Ugh. So here's what happens. So before you write this down, I'm gonna point something out. So I'm gonna write out the top. I'm gonna have x squared over x squared times x plus h squared minus x plus h squared over x squared times x plus h squared. But then instead of writing all of that divided by h, I don't love fractions and fractions, so I'm going to write all of that times 1 over h. If I'm dividing by h over 1, that's the same as multiplying by the reciprocal 1 over h. Do be careful with this. I've seen too many students say you're multiplying by h, not multiplying by 1 over h. Right? If you're dividing by something, that should never be the same as multiplying by the same thing. You're always multiplying by the reciprocal of your denominator. So now let's simplify things. And again, something to be aware of. There's only one h I'm trying to make cancel out. That one right there. This other stuff in the denominator here, no good can come of multiplying out the denominator in this problem. You're going to be wasting your time because the denominator is kind of set in stone as to what it is. Multiplying it out, nothing in it's going to cancel out. But eventually, we're expecting that h to go to 0. So multiplying out is just kind of a waste of your time because you wouldn't have had to do it anyway. But we do want to multiply out this x plus h squared because we need stuff in the numerator to cancel out so that we are left with just h's in the numerator so that we can cancel out the one h we need to cancel out. So here's what we should write. We should write, first of all, one big fraction because that's why we got a common denominator so that we can add or subtract these fractions together. Right? That's the whole point of getting a common denominator, is to be able to add the fractions or subtract the fractions. So the denominator there is going to be x squared times x plus h squared. On top, I'm going to have x squared minus all of, when I multiply out x plus h times x plus h, I get x squared plus 2xh plus h squared. And then I could write times 1 over h, or I could just toss the h into the denominator. Totally valid. Right, multiplying fractions together, you multiply top times top, bottom times bottom, and the top times 1 is still the top, and the bottom times h is what we have. All right, we're almost there. So limit as h goes to 0. The x squared minus x squared goes away, but don't forget to distribute this minus sign to the other terms in the numerator. So we're going to be left with a minus 2xh minus h squared over x squared times x plus h squared times h. Factor out an h from the top. You're left with the limit as h goes to 0 of h times negative 2x minus h all over x squared times x plus h squared times h. Finally, this h divided by that h is 1, and we can let the rest of the h's go to 0 and get negative 2x minus 0 over x squared times x plus 0 squared. Skip that step and get negative 2x over x to the fourth, which reduces to negative 2 over x cubed. Or if you prefer, negative 2 times x to the negative third. Exactly what we were expecting to get. So obviously the power rule is super useful because doing this is time consuming, right? We don't want to be doing this for lots of derivatives because it just takes a lot of time. But it is important to believe, right? Okay, yeah, the power rule does work, right? We have seen for quite a few examples now that whenever you take the derivative of x to some power, you end up multiplying by that power, and then your new power is one less than your old power. So if your original power was positive, it's going to be less positive. If your original power was negative, it's going to be more negative when you subtract. Cool. So let's look at some examples. Because yeah, why am I looking here? I already know what the example is. I just feel like I should look just to be sure I'm not doing something totally crazy. Yeah, of course. So let's take some derivatives of more, not really more complicated, but seemingly more complicated things. For example, we're going to use the power rule to find the derivative of f of x for the following question. Say, let's see, we have f of x equal to x to the 12th plus 1 over x cubed plus the fifth root of x to the fourth. And before we can do any of this, we need to rewrite. Here's a good point. So I don't even want to write this down, but what I've seen students do sometimes, which I would strongly encourage you not to do, is they'll take the derivative of x to the 12th because it's already something you take there. So they'll write the next step is like 12x to the 11th plus x to the negative third plus x to the 4/5 power. So because they're differentiating one part and simplifying the other part, and that's not great. It's actually bad. I will say it's bad. You should either be only simplifying or only differentiating, but you don't want to mix the two things at once because then you're writing something that's not really correct because it's not the function because you've simplified part of it, but you differentiated part of it. And it's not the derivative because you haven't differentiated the whole thing. So I would say before I do anything, and this is good advice in general, if you have to take the derivative of a function, first simplify it as much as you reasonably can. So just simplifying, I'm going to have f of x equal to still x to the 12th, but this is going to be x to the negative third. This is going to be x to the 4/5 power. And now we've got each x to a power, so we can take the derivative really easily and get f prime of x equal to 12 times x to the 11th minus 3 times x to the negative fourth plus 4/5 times x to the 4/5 minus 1 is 4/5 minus 5/5, which is negative 1/5. And that's your answer. In a similar way, I would like all of you on your own to find the derivative of 5 times x to the 6th plus 6 times the square root of x minus 8. And you might, not might, you should rewrite it first, or at least think about how the square root of x is x to some power. All right, let's take a look and see here. So for my derivative, what's the derivative of 5x to the 6th going to be? Anyone want to share? Yeah, right, 30x to the 5th. And for 6x to the 1/2, what are we going to get? I know you know. It just like, no one wants to know. Okay. We're going to get 6 times 1/2, which is 3 times x to the negative 1/2. Minus 0. Not that you need to write that, but it's good to recognize that the derivative of that 8 is just going to be 0. And I want to point out that we just used two rules that we haven't even talked about. It's totally fine. These are rules that you use all the time without ever thinking about using them. But what we really just did, we said, well, first of all, for the first one here, we used the rule that when you take the derivative of a bunch of functions added together, you just take all the derivatives and add them together. Similarly, here, we use the rule that if you have the derivative of a constant times a function, you end up getting the constant times the derivative of that function. Because really, this part right here, even though we didn't write it that way at all, this is really 5 times 6x to the 5th. The derivative of 5 times x to the 6th is 5 times the derivative of x to the 6th. And I'll say again, these are rules you're going to use all the time without even thinking about the fact that you're using them, which is what you should be doing. But I will write them down here because I do think they're worth saying words about. So the two rules we have used, or actually the three rules technically, is that the derivative of f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x. And it's true whether it's addition or subtraction. So the derivative of f plus or minus g is equal to the derivative of f plus or minus the derivative of g. And the other rule we did was that the derivative of a constant times a function is equal to the constant times the derivative of the function. We'll talk more about this rule later on, the constant multiple rule, but I will say these words often. When you have a constant multiple, that constant multiple likes to hang out. When you have a constant on its own, like -8 there, its derivative is 0. But that 5 right there times x to the 6th, when we take the derivative, that 5 hangs out, and you multiply it by 6x to the 5th. I really like to use that language because that idea persists throughout the second and third quarters of calculus as well, where constant multiples, whether it's for a derivative or an integral or a series, they like to hang out. So keep that idea in mind because it's going to be true for a long, long time. Cool. What else have we got? Oh yeah. So a couple other things. Not yet. So at the stage where you don't have sort of any other tools available to you, if you're asked to find the derivative of something like f of x equal to x squared times x cubed plus 1 squared. Oops, sorry, you can't see that. Apologies. I zoomed in too much. If you're asked to find the derivative of something like that, and you don't have a product or a chain rule available to use yet, you just have to multiply it out. So here, and in fact, I'm going to repeat what I said because I want you to hear it as well. So the thing I was saying just before is that when we take the derivative of a constant times a function, you get the constant times the derivative. And as I will say, and everyone else will be saying already, constant multiples hang out. They stick around. They don't go away. Over here. So here, though, before we can take the derivative, we have to simplify it. So we're going to rewrite this as x squared times x cubed plus 1 squared. And you should get comfortable just squaring something out without writing it out. It's going to be the first thing squared, so x to the 6th, plus 2 times the first thing times the second thing, which will be 2 times x cubed times 1, plus the second thing squared. And then distributing the x squared, we're going to get x to the 8th plus 2x to the 5th plus x squared. And now we're ready to take the derivative and get 8 times x to the 7th plus 10 times x to the 4th plus 2 times x to the 1st. A similar idea is true for this function. F of x equal to 7x cubed plus 6x plus 8, all divided by 2x squared. Specifically, if you have a quotient, where the denominator is a single term, right? You don't have like x squared plus 1 or 2x squared minus 5, right? If it's just one thing where you don't have plus or minus anything else, you can divide each thing in the numerator by the thing in the denominator. So we can rewrite this as 7x cubed divided by 2x squared plus 6x divided by 2x squared plus 8 divided by 2x squared. And then simplify that as, let's see, 7 over 2. I'm just going to leave it 7 over 2. You can write it as 3.5 if you prefer. X cubed divided by x squared is just x to the first. 6 divided by 2 is 3. X divided by x squared is x to the negative first. And 8 divided by 2 is 4. X to the 0th, or no x is there, divided by x squared means you have an x to the negative second. Okay, we've done all this. So make sure you still then do the thing you're supposed to do, right? We simplified it, and now we need to take the derivative. So our derivative is going to be 7 halves minus 3 times x to the negative 1 minus 1 is minus 2 minus 8 times x to the negative 2 minus 1 is minus 3. You can write plus negative 8, but it's better just to write minus 8 or plus negative 3, but I'd rather write minus 3. Yeah, cool. Sure. Other functions. Yeah. What time we got? Okay. Let me look at my list here of things I want to make sure I say. Sure, we did that. We did that. We did that. Cool. So just to kind of summarize so far what we've said, just to make sure that everyone's seen all the things. So we've talked about how the derivative of x to a power is equal to the power times x to the power minus 1. I don't know if I, oops, sorry, again. I don't know if I explicitly said it, but I won't say it now. The derivative of any constant is going to be equal to 0. Interesting point. Sometimes you might see someone ask you to find, like, say, my function is, what kind of annoying example do I want to pick? My function is pi to the third power. You know what the derivative of that is? 0. Because pi cubed, although I don't know what it is, it's a constant. It doesn't have any variables in it, right? There's no x's in there. So that derivative has to be 0. Because pi cubed is, I don't know, it's like 29 or something, approximately. But it never changes. And then the other one I mentioned was the derivative of a constant times a function is just the constant times the derivative of the function. And the derivative of the sum or difference of functions is the sum or difference of the derivatives. Cool. All right. Yeah. Sorry, I'm just debating which direction I want to go next. I guess we should talk about the product rule. Yeah, product rule. Yeah, yeah. Oh, thank you. Yes, good call. Yeah, yeah, product rule. Let's do product rule. So let's talk about the product rule. Let's not yet. Sorry. I just remember why I don't like to do it yet. So let's talk about three other functions first. Maybe two. Let's use it. Yeah. Well, I'm going to leave this page over here. Maybe I'll come back and put more stuff on it later. So, yeah, let's talk about the derivative of sine of x. Now, there's a couple ways to think about this. One way is using the limit definition, which we will talk about in a second. But I want to point out this is an excellent time to think about how things work graphically. So I'll remind you that the derivative of a function at a particular point is just the slope of the tangent line at that point. So let's actually look at this graphically. And I'm going to want to draw a graph below this graph. So give yourself room to draw another graph below the graph you're drawing. Try and make things look relatively straight on here. So sine of x has a period of 2 pi, has a range of -1 to 1, Starts at the origin. At pi over 2 is 1. At pi is equal to 0. At 3 pi over 2 is negative 1. And 2 pi is back to 0. And it looks like, sorry, where'd you go? Yeah. Looks like what you know it looks like already. It's your usual sinusoidal shape. Sinusoidal just means it looks like sine or cosine, because really sine and cosine look the same. They're just shifted from each other. So now, if I want to graph the derivative of sine, I'm just going to start by finding the slope of the tangent line at some convenient places. Specifically, in fact, if you're ever asked to do this just in general, the best thing to do first, if you're ever asked to like from a graph try to graph the derivative, is to look for where the graph has a horizontal tangent line. So I'm going to point out that right here and right here, the slope of the tangent line is 0 because the tangent line is horizontal. Meaning, if I'm graphing the derivative down here, well, I'm going to look at those points and say, great, I know that right here at pi over 2, the derivative is going to be 0. And right over here at 3 pi over 2, the derivative is also going to be 0. So look for the places where the derivative is equal to 0 first if you have to graph the derivative. It's usually the easiest thing to find. Now, what about over here? Well, sorry, I keep pushing this around. Over here, the slope of the tangent line is it positive or is it negative? Definitely positive. And I will tell you it's positive 1. Hopefully my graph is agreeing with that. And similarly, over here, the tangent line is negative. It's a negative 1. And not that any of you should really care at this point, but I will point out that this tangent line I drew is not great. This tangent line is better because those tangent lines to those points technically should go through the graph because those points are technically inflection points. So, but don't too worry about that too much. I just want to make sure that you didn't like other tangent lines not so great. Sorry. So anyway, at this point here, the slope of the tangent line is negative 1. And then back here at 2 pi, we've gone through one full cycle or period, so the slope of the tangent line is back to positive 1. And hey, look, this graph going through these points looks awfully familiar. You know what it is? It's good old cosine. Exactly. So there's a nice way to see that the derivative of sine is equal to cosine, or at least to visually believe it. In a similar way, you could, I should have said more about leaving yourself some room here, but if you try to draw the graph of the derivative of cosine, yeah, I feel bad about trying to squeeze this in here, but not bad enough that I'm not going to do it. You try to squeeze in the graph of the derivative of that. Let's see. So now the slope of the tangent line here is 0, and here is 0, and here is 0. So we've got, sorry, I know it's not the best, but I think it is worth seeing right now. So we've got a 0 here, and a 0 here, and a 0 here. And then at pi over 2, the slope of the tangent line appears to be negative 1. And at 3 pi over 2, the slope of the tangent line appears to be positive 1. So we have a graph that looks kind of familiar. It looks like I've taken the sine graph and flipped it over. Or in other words, I have negative sine. So the derivative of cosine, or the second derivative of sine, is equal to negative sine. Kind of great. I really do encourage you to keep this graphical example in your mind or at your disposal because I think it's a nice way to remember, oh yeah, the derivative of sine really is just cosine. It's not that bad. That said, it's probably worth seeing the limit definition as well. So I don't imagine you ever need to repeat or reproduce this, but I could be wrong. So write this down or don't, whatever you like. But just using the limit definition here, derivative of a function of x is going to be the limit as h approaches 0 of the function evaluated at x plus h minus the function of x divided by h. And at this point, you're like, well, what do I do now? Well, this is where you have to use the angle sum identity for sine, which I know I did mention a couple of classes back because I was like, someday we're going to talk about this. Well, today's the day. So I'll remind you all that sine of x plus h, or sine of an angle plus another angle, is sine of the first angle times cosine of the second angle plus cosine of the first angle times sine of the second angle. So it's going to look like this. It's going to look like the limit as h approaches 0 of sine of x times cosine of h plus cosine of x times sine of h minus sine of x, all divided by h. And now what we're going to do, again, let me just pause a second. You haven't done this in class, right? Great. Not that I shouldn't show it to you anyway, if you've already done, but it's good. I like being the one to show it to you first because I feel if I'm repeating it, it just feels like, well, we already saw this weekend. But now you can see it this time, and if you see it again in class, be like, yeah, I know what's going on already. So here's what we're going to do now. We're going to try to group together pieces that we can deal with. Specifically, since I see a sine of x here and a sine of x here, I'm going to put those two pieces together and then factor out the sine of x. So right now I'm going to rewrite this as the limit as h goes to 0. So I want these two pieces. So the sine of x times cosine of h minus the sine of x, all divided by h. And then I want this piece as well, the cosine of x times sine of h over h. Oh, sine of h over h. That looks familiar. That seems like a good sign. So let's actually do two things at once in this next step here. We're going to get the limit as h goes to 0. In this first piece here, I grouped the things together that had the same term, sine of x, so that I could factor that sine of x out. Or at least that seems like a reasonable thing to do. Yeah. So I'm going to factor out a sine of x, and I'm left with cosine h minus 1 on top over h on the bottom. Over here, I'm going to factor out, or I'm not even factoring, I'm just going to rewrite it as sine of h over h times cosine of x. Totally legit. Okay, here's what I'm going to say, but I'm going to show a few more steps. So here's what's going to happen. Show me on your fingers. What's the limit as h goes to 0 of sine h over h? Right, 1. Okay, you might not know this other one as well. What's the limit as h goes to 0 of cosine h minus 1 over h? Yeah, it's 0. We can talk more about that in a minute, but let's just leave it. So what a person not showing any more steps than they needed to would say it's sine of x times 0 plus 1 times cosine of x, which is going to be cosine of x. I will point out this is a place where we're using some of those limit rules that we kind of didn't really talk a whole lot about. Because what we're really doing here is saying the following. As far as h is concerned, in fact, let me actually back up. I'm going to break this up as my room, I'm slowly running out of room here. The limit as h goes to 0 of sine of x times cosine of h minus 1 over h plus the limit as h goes to 0 of sine of h over h times cosine of x. Right, it's totally fine to say the limit of a sum is the sum of the limits. And then constant multiples like to hang out. And although it's kind of weird to say, as far as h is concerned, sine of x is a constant and cosine of x is a constant. So we're going to rewrite this one more time as sine of x times the limit as h goes to 0 of cosine of h minus 1 over h plus, here we're going to pull out the cosine of x times the limit as h goes to 0 of sine of h over h. And then finally we can say, oh yeah, that's going to be sine of x times 0 plus cosine of x times 1, which is just equal to cosine of x. Whew. So that's a very rigorous showing of why the derivative of sine is equal to cosine. But again, I think it's good to have seen. I don't think it's necessary for you to reproduce this unless your teacher says otherwise. I don't imagine that, but some people do things I don't imagine, right? Like my imagination is not that great. Sometimes people do crazy things like, wow, never thought I would have done that. So derivative of sine is cosine, and we won't show it, but in a very similar way, you could show that the derivative of cosine of x is equal to negative sine of x by using an angle sum formula and doing the same sort of thing. It's kind of neat. Cool. Yeah. Yeah. So now that we have said that, we can get to what I actually want to say, finally, which is the following. Sure. Yeah. So what I really want to answer the question is if your function is something like x cubed times sine of x, what's the derivative equal to? Well, I'll tell you what it's not equal to. Don't even write this down. The derivative is not equal to 3x squared times cosine of x. Or in other words, if you're taking the derivative of a product, you cannot differentiate each part and multiply the result together. Products and quotients require more than just differentiate each part. How do I know this is true? What's my proof? Well, here's some evidence. What if your function was x cubed times x to the fourth? Which I know we could simplify, right? Over here we can write f of x is equal to x to the seventh. What's the derivative of x to the seventh? It's like, you know what it is. 7x to the sixth. Okay, I'll point out that the derivative of this is definitely not 3x squared times 4x cubed. Because 3x squared times 4x cubed is 12x to the fifth. And those are not the same. So there's some good evidence that, oh yeah, if you have a function, even this one you could simplify like this, where it's something times something, we cannot differentiate each of the somethings and multiply the result together. That does not get you to the right answer. So we have to use what's called the product rule. And we will show it in a second, but I'll point out, here's how it works. So if your so here's how the product rule is actually going to work. So if your function is x cubed times x to the fourth, just to make it real easy, and people often like to give these things names like f and g, but I've already used f. So let's call them u and v. I don't know why someone chose u and v once upon a time as a standard choice, but it is kind of a standard choice, and which is terrible because they look similar and it's easy to confuse them with each other, but whatever. So here's what we're going to get. The derivative is going to be the derivative of u times v left alone plus switch it up. Leave u alone, multiply it by the derivative of v. Let's see what we get here. So the derivative of the first thing is 3x squared times leave the other thing alone, plus now we leave the first thing alone, x cubed, multiplied by the derivative of the second thing, which is 4x to the third. And let's see what we get when we simplify this. We get 3x squared times x to the fourth was 3x to the sixth. X cubed times 4x cubed is 4x to the sixth. And we add those together, we get 7x to the sixth, which is the actual derivative. Cool. So there's some really good evidence that, oh yeah, the product rule does what it's actually supposed to do. So here is the product rule written more generally. Let's see if I use, yeah, sure. So here's the product rule. Product rule says the derivative of f of x times g of x is equal to the derivative of f of x times g of x left alone plus f of x times the derivative of g of x. I always think of it as you differentiate one thing, you multiply it by the not derivative of the other thing, and then vice versa, and you add them together. I will emphasize that when you're thinking product rule, you better have a plus sign in the middle somewhere, right? You are adding these two pieces together. I've seen many, many people over the years forget there's a multiplication and multiply it all together, which is not at all what we want to do. So back to the question that started this all. If my function is x cubed times sine of x, what's the derivative? Well, the derivative is going to be f prime of x equal to the derivative of x cubed times the other function left alone plus the x cubed left alone times the derivative of the other function, and the derivative of sine of x is cosine of x. Neat. What time is it? Okay, not that much time left. Sure. So let me ask you all in a similar way, find the derivative of x to the sixth times cosine of x. Shouldn't be too terrible. If you find it helpful, you can do something like, say you're thinking of this as f and this is g, and your derivative should be f prime times g plus f times g prime. So let's see, what do we get here? We get f prime is 6x to the fifth, g is just cosine of x, plus f is x to the sixth, and g prime is negative sine of x, which you do need to put parentheses around. Otherwise, it looks like you're saying x to the sixth minus sine of x. What I really should have done was I should have thought ahead so that I didn't have to rewrite it, but I really should write my final answer as 6x to the fifth times cosine of x minus x to the sixth times sine of x. Probably a better way of writing that. Not probably, it's definitely a better way of writing that. Something I will say about the product rule is that for the product rule, the order doesn't matter. Meaning, most people are going to say it's something like f prime g plus f g prime, but it's also fine to write f prime g plus g prime f, or g prime f plus gf prime, right? Because the order of multiplication doesn't matter and the order of addition doesn't matter. Or what I should really say is the order of addition is commutative, meaning you can interchange it and you still get the same result. And the order of multiplication is commutative, meaning you can interchange it and get the same result. So I usually think of it like this, but some people think about the derivative of f times g as instead of f prime g plus f g prime, they might write it as f prime g plus g prime f, or gf prime. That's dumb, but fine. Plus fg prime. Like you can interchange things to your heart's content and still be right. That is not true when it comes to the quotient rule, which is why, even though you can do this any way we like to, we kind of prefer this first way because doing this first way has the most in common with how the quotient rule looks. So that's kind of why we would think about it that way. Running out of time. Okay, so sure. Sorry, I'm trying to think about what I want to say here. Yeah, let's go ahead and hit the quotient rule. So, in a similar sort of way, the quotient rule says the following. If you want to find the derivative of f of x divided by g of x, okay, people write it like this. I'm going to tell you how I say it though. So it's going to be f prime of x times g of x. People often leave off the x's here and just say f prime times g because it's more convenient to write it that way. So if you want to write just f prime times g, you don't have to write the f prime of x times g of x minus f of x times g prime of x divided by g of x squared. Or as I will typically say, now notice here that when I say this, it's going to be slightly out of order. In that instead of saying f prime times g, I'm actually going to say g times f prime. Totally fine to interchange the order of multiplication. But what I really actually say is it's the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Those are the words that will come out of my mouth when I talk about the quotient rule because it's just the way that it's in my head that way. Like there are lots of other ways of saying it. There's like there's a song or something. I don't know. Some people say low D high minus high D low, all divided by low squared. High for the high function, low for the low. D high, D low, meaning the derivative of the high or the derivative of the low. Um, as long as you can remember it the right way, it doesn't matter how you remember it, as long as it's the right way. So, for example, and we're running out of, yeah, sure. So, just to kind of show you another example of why this is true, if I wanted to find, say, the derivative of, not equal to, James, the derivative of, so the derivative of x to the seventh divided by x squared, we already know what the answer is. Or with a little bit of thought, we know the answer. X to the seventh divided by x squared is x to the fifth, and the derivative should end up being 5x to the fourth. But let's do it using the quotient rule so we can see that the quotient rule actually does produce the expected result. So it should be the bottom times the derivative of the top, which sometimes I'm just going to write as the derivative of the function as opposed to actually saying it's 7x to the sixth, minus the top times the derivative of the bottom, all divided by the bottom squared. Now let's simplify it and see if we get the right thing. So it's going to equal x squared times 7x to the sixth minus x to the seventh times 2x divided by x to the fourth. That's going to be 7x to the eighth minus 2x to the eighth divided by x to the fourth. That's going to be 5x to the eighth divided by x to the fourth. And that's going to be 5x to the fourth, as expected. Cool, it works. But then you can ask questions to find the derivative of functions that you cannot just simplify. For example, we could ask ourselves, like, what's the derivative of x cubed plus cosine of x divided by x to the fourth minus 1? And now you're kind of stuck having to use the quotient rule. I'll say, kind of aside here, technically you never have to use the quotient rule. Once you know the chain rule, you could always avoid using the quotient rule. That said, you shouldn't. It's still preferable to use the quotient rule, I think, than to avoid it using the chain rule. But technically, if you really, really hated it, you could never use it again in your life. But we should. So let's see. The derivative of this is going to be the bottom function times the derivative of the top function. Let's actually just take the derivative here. The derivative of the top function is going to be 3x squared minus sine of x minus the top function times the derivative of the bottom function, which is going to be x cubed plus cosine of x times the derivative of the bottom, which is 4x cubed. I guess technically I didn't need to write parentheses around 4x cubed, but it's not a bad idea to write parentheses around each of these things for these ones. I will point out, if you don't write parentheses around the x to the fourth minus 1 or the 3x squared minus sine x or the x cubed plus cosine x, it is wrong because you're not getting the multiplication in the right spot. And then finally, divided by x to the fourth minus 1 squared. And there's not really any good reason to simplify this. Most of the time on an exam where you're asked to find derivatives using the product quotient chain rule like this, usually the instruction will be like, find the derivatives and do not simplify them. Because they really just want to see that you're able to apply the rules correctly, differentiate correctly, and it's not a test of your ability to simplify things yet. So make sure in general, but specifically on this next time, make sure you always read the instructions to your exam carefully because they will say words that often change how much work you have to do.